Good morning, everybody, and welcome to the G2M webinar on the need for speed, NVMe, NVMe over Fabric, and data processing accelerators. My name is Mike Human. I'm with G2M Research. We have three panelists with us. I'll introduce those guys in a second. Let me kind of walk through the ground rules and kind of the way we operate the webinars and the agenda. So I'll talk for a little bit, then we'll have a presentation by each of our three presenters. Those will take us to about the bottom of the hour. Then we'll have a couple panel discussion questions. In and amongst those questions, we'll have a couple audience surveys. You can use the Zoom audience survey window to answer those. They're all anonymous, so don't feel like we're going to record your answers or anything like that. And then finally, we'll wrap up with an audience Q&A. Zoom has a Q&A window. If you've used it before, that's where we'd like you to put in your questions, and we will answer them. We'll hold them all to the end and answer them then. And that's kind of the way we'll go. One other thing is that this is kind of an important part. The webinar is going to be recorded, so everybody who's registered will get a link to the recording in a couple days. You'll also get a PDF of the slide sets. So with that, let's go ahead and get started. So the need for speed in today's workloads, it's not too hard to remember, say 10 or 15 years ago when, storage was slow, networks were slow, even processors were slow. And then we've had a lot of things happen that have really changed that. If you look at today, for instance, we have a lot of different capabilities of things like VMware and capabilities like that, hitting 100% processor utilization. With NVMe-based flash devices, we have very high-speed storage. And NVMe over Fabric really extends that via a number of different physical protocols across the network. Of course, we have very fast networking today. 100 gigabit Ethernet and beyond is not surprising. InfiniBand has speeds even higher than that. But at the same time, there's been a lot of interest in building accelerators. A lot of companies have been focused on that. And there's kind of three basic reasons. If you look at kind of the higher level networking protocols, things beyond L2, which is kind of where the switches are generally focused, and custom protocols have been developed for a lot of different workloads. All those, for the most part today, are done in the CPU. So what people are trying to do is move that workload off the CPU so they can use the CPU for, in the case of the cloud, revenue producing operations, or in the case of enterprise data centers, to do the work that they bought those servers for. Similarly, in the storage world, though, NVMe and NVMe over Fabric are adding a lot of new capabilities, and some of those, in fact, do put snapshot onto the CPU itself. Then you throw in all the other fun stuff, right? Like security, data resilience, doing snapshots, copies, things like that. All those things take cycles away from the CPU, and you get back to the point where only half of your CPU is available for workloads. So that's why a lot of these companies are looking at a lot of these different capabilities. Jump a few slides ahead. If you look at where a lot of this work is being done, a lot of it's being done by the hyperscalers. Think of AWS, Azure, Google Cloud. They're putting lots of money and resources in accelerating a lot of their workloads. Annapurna Labs was one of the early pioneers in this. They were purchased by AWS several years ago. Whole families of accelerators are used in the AWS cloud. Azure has also, for Microsoft, done a lot of this work as well, especially around the networking stack, but also neural networks and storage. And in addition to that, you've got a lot of SSD vendors who have provided capabilities like software-defined flash that allow large people with large budgets abilities to customize their flash storage to do what they want. So the real question is, okay, if you're not a hyperscaler, what can you do to accelerate your own workloads? And that's what we're really here to talk about today. So joining me today, we have Rob Davis. Rob is VP of Storage Technology at NVIDIA. We also have Peter Nufrick. Peter is an Intel Fellow, and he's representing NVMe.org today and talking a little bit about what things they've done to help speed up operations. And then finally, I have Tony Afshari. Tony is VP of Marketing at PlyOps, and he's going to talk about what PlyOps is doing there as well. So with that, let me give it to Rob. Rob, let me give you control. You should be good to go.
Thank you, Mike. Thanks also for inviting me to be on your webinar. Good morning, everyone. At NVIDIA, we are all about speed, probably no surprise to many of you. And we are also all about using accelerators and NVMe and NVMe over Fabric to get the most possible storage performance for our GPUs. Here's some of the ways we're doing it. One of the platforms for many of our storage accelerators is called a DPU. I'm guessing DPUs may be new to some of you. They are a new player in the data center. In this industry, we love acronyms, and DPU stands for Data Processing Unit. Like the GPU, which accelerates compute for the CPU, the DPU accelerates data movement for both the CPU and the GPU. But more than that, it adds security to protect that storage from unauthorized access with little effect on performance because of its accelerators for encryption and user isolation. Just FYI, on many of my slides, I have links where you can find more detailed information on what was covered there. DPUs are designed to offload, accelerate, and isolate data center workloads. All kinds of data center workloads, some of them that are listed here. But for this talk, I'll be focusing on NVMe-based storage workloads. The NVIDIA DPU is based on an ASIC called Bluefield. The major components are our ConnectX network adapter and PCI switch for I/O, an ARM CPU, a RISC-V processor, and multiple hardware data accelerators. The ConnectX 7 RTL is integrated into our latest Bluefield ASIC called Bluefield 3. It supports 4 network ports with speeds up to 400 gigabits per second on both Ethernet and InfiniBand. Bluefield 3 has a multi-core A78 Hercules ARM CPU with DDR5 memory interfaces. Also, a multi-core RISC-V processor for programmable data path acceleration, and a Gen 5 PCI switch for local connectivity. Last are our accelerators, which are hardware engines for offloading the ARM, RISC-V, or host CPU from cycle-intensive or low-latency dependent functions. You can check out more details on the Bluefield 3 spec on that ULR at the bottom. Let's look deeper at some of those accelerators. One of them does target-side NVMe over Fabric protocol offload. On a storage target, like a JBoF, that's shown here on the left of the slide, there's typically a CPU that sits between the network ports and the NVMe SSDs. It's running software. So that x86 is running software that basically converts NVMe over Fabric's protocol on the network ports to NVMe on the PCI bus and then back again or vice versa. This software is made up of the network adapter driver, the NVMe over Fabric stack, the operating system block layer, and the NVMe SSD driver. Incoming NVMe over Fabric requests to the JBoF first land in the network adapter with the NVMe command encapsulated in the NVMe over Fabric protocol. The network adapter passes it to the driver software running on the CPU, which passes it to the NVMe over Fabric stack, which de-encapsulates the command, the NVMe command. The NVMe command then goes through the driver to the SSDs, then to the NVMe SSD controller. The response then follows the reverse path through the software. Not a lot of complicated software really, but when you run millions of IOPS through it, it uses a lot of CPU cycles. With the Bluefield DPU-based NVMe over Fabric target accelerator on the right side, instead of those millions of IOPS burning CPU cycles, the accelerator takes on the load in ASIC gates. The software stacks are still there in the ARM to handle exceptions in management traffic, but not the data path. The Bluefield hardware engine is now de-encapsulating the NVMe commands and writing it directly into the submission queue of the SSD, then monitoring the completion queue for the response. Here's the difference in performance between using the accelerators versus the CPU running software. The reduction in latency by removing the software from the data path is 3x. And this, of course, is also reflected in the IOPS increases. And the effect on CPU utilization across the block sizes is even more dramatic. At first glance, in fact, you don't even see the offload CPU utilization because it's barely measurable. Here is an NVMe over Fabric accelerator for the other end of the storage data path in the initiator. Almost all servers today can support NVMe SSDs in all operating systems. Called Snap, what this accelerator does is make the blue field plugged into any system look like an NVMe SSD. This makes migration of applications to network-based storage transparent. You can even hide the local storage behind the NVMe emulation by connecting it to the DPU PCI switch. And Snap also supports other storage emulations too, like VirtIO block and VirtIO file, all accelerated in the DPU ASIC. Other than increasing performance and flexibility, there is another reason this is important. Because now there is a hardware security barrier between the storage and unauthorized users, controlled not by the user CPU, where it could be hacked, but by the Bluefield CPU, which is inaccessible by the user behind the hardware emulation. Bluefield also has encryption accelerators for most encryption algorithms. They are very flexible and can be used across the storage data path. One place is inside the JBOF or all-flash array on the SSDs for encryption of data at rest with the AES encryption algorithm, or it can be done on the network ports for encryption of data in flight with algorithms like IPsec or TLS or MACsec. Now let's look at some examples where these accelerators have been used and the value they provide to the end user. Here, the DPU not only accelerates the performance of a vast storage system, but also reduces the power, real estate, and weight of the JBOF component. All of these obviously contribute to lowering the total cost of ownership, the TCO of the data center they are deployed in. In this example, just focusing on the DPU's encryption accelerators, you can save 34% on the power cost with IPsec encryption, which, as you can see at the data center scale over many years, can add up to real money. For computational and edge storage, we have a special DPU we call a converged accelerator. It mixes a Bluefield DPU and Ampere GPU on the same PCI adapter. It can be used for accelerating edge computing NVMe storage applications plugged into a JBOF. The AI application running on the GPU decides what edge data is important enough to be sent over the slow wide area network back to the main data center for a deeper look, while the DPU accelerates, manages, and secures the data collection process. AI applications are often challenged by storage performance requirements. This is not only because of the enormous size of the data set, but often needs to be moved to the GPU, but also because of how fast GPUs can process the data they are given. If you compare the amount of time it takes for a CPU to process and perform its storage I/O cycle to that of a GPU, as we do on the left side of this chart, you can see the issue. If the I/O speed is the same, the GPU will be waiting for data to be loaded or the results of its calculation to be stored. In order to efficiently use the GPU, you must accelerate the storage I/O performance. To solve this, NVIDIA developed a technology called GPU Direct Storage. It uses the RDMA accelerators in Bluefield or ConnectX to decrease the storage I/O cycle for the GPU. Without GPU direct storage, remote data and local data is moved from the remote or local SSD to the GPU memory with a couple stops in system memory and lots of software. This is shown with the red lines. But with GPU direct storage, the green lines, local and remote data is moved with RDMA or DMA directly to the GPU memory via the RNICs or the CPU DMA engine on both ends of the RNICs on both ends of the network. This provides a big improvement in bandwidth and reduction in latency for data-intensive AI applications. We have covered some of the ways we use DPU accelerators at NVIDIA to get the most secure performance out of NVMe and NVMe over fabrics. And we've also looked at how we use GPU direct storage to accelerate NVMe and NVMe over fabric storage for our GPUs. Last, let's look at the latency ramifications of NVMe storage and the network used to make NVMe over fabrics out of it. Here is the combined latency of some common Ethernet switches and NICs compared to the performance of different NVMe SSDs. And NVIDIA Ethernet and InfiniBand NICs and HCAs and switches. Both can run NVMe over fabrics, but ours are designed with the latency reduction acceleration needed to get the most out of NVMe-based high-performance storage. Look what happens when we add a typical network architecture to the equation, here like a 3-tier Klaus architecture. The latency numbers of the networking components are multiplied by 3 because of the 3 hops. And remember that NVMe over fabrics is a request response protocol. So now you double that. And if there is a speed mismatch between the network components and the switches don't support adaptive cut-through acceleration, more latency is added. Now, if there's congestion and the switch doesn't support adaptive routing acceleration, even more latency is added. Suddenly, by not paying attention to your network components, you have given up much of the performance you bought NVMe SSDs for in the first place. And with that, I will turn it over to Peter.
Thanks,
you, Rob.
Peter, let me give you control real quick here. All right, it should be yours.
All right, great. Thank you. So I'm going to give you a quick overview of what's happening in NVM Express and about acceleration and performance within NVM Express. So, NVMe was architected from the ground up for high performance. The architecture has no practical limit on the number of outstanding commands. We support up to 64,000 IO queues with approximately 64,000 commands each. So there's a lot of outstanding commands. We support many core architectures, so you can allocate queues and interrupts to each core, which eliminate the need for locking. We have a very efficient doorbell mechanism, so unlike storage protocols prior to that, which required reads, you can do everything with writes. We have fixed size commands and completions, which make command fetch, decode, and execution very streamlined and high performance. Finally, NVMe supports out-of-order command processing and data delivery. So all of these things were done for PCIe SSDs, and in 2011, we introduced NVMe around PCIe SSDs. At that point, NVMe started growing, and we got a request to extend the NVMe architecture to Fabric. So in 2015, we released NVMe over Fabrics, which supported NVMe over RDMA and NVMe over Fiber Channel. Then a couple of years after that, there was a desire to run NVMe over standard fabrics, not something special like a Fiber Channel or RDMA fabric. So we extended NVMe again to support NVMe over TCP. And the really surprising thing about NVMe over TCP is that we saw systems being built whose performance and latency were very close to those of direct attached systems. So to think about it, we started with NVMe like a strict down Formula One racing car. It was optimized for speed. We removed every ounce of overhead to try to get the absolute best performance for the SSDs, PCIe SSDs that first came on, and we carried that architecture going forward through our design. But as any storage protocol, we needed to add things, so first we started with an NVMe base specification, which is optimized for PCIe. Then we added fabrics, we added commands, we added management, and then we saw a need for evolution of the NVMe architecture. So we introduced the NVMe 2.0 family of specifications. A lot of people think NVMe 2.0 is about some big new feature, but it was really about re-architecting the specifications. And the first thing, there were 3 reasons we did this. The first was the NVMe architecture was getting pretty complex. We had fabrics, we had different command sets, we had management, and if somebody just wanted to build an SSD, they should be able to pick up the specs and read how to build an SSD. Alternatively, if they wanted to build a fabrics device, they should be able to pick up those pieces. So we did that to simplify use of the technology. The second piece is we wanted to enable rapid innovation, right? So, when we first developed NVMe, it was a Formula One racing car. People had new ideas that they wanted to add to NVMe, and we didn't want to go through and modify the core architecture of that. So by refactoring the specifications, we can now add things to the specification. If they succeed, great. People will read those specs, and if they don't, then it just becomes a specification that's available that people can reference in the future or not, but the industry doesn't need to execute. Finally, it creates a extensible infrastructure for us to manage the specifications. So, that's, sort of inside baseball about NVMe. Let's talk about performance. So first thing that we did to enhance NVMe performance is we added a lot of the features to the Formula One racing car. So, an example of this is copy. Initially, we didn't have a copy command. Later, we added a copy command. Next, in NVMe 2.0, we enhanced the copy command to allow you to copy across namespace. We're in the process of finishing up more copy enhancements now that will be available shortly, and we've got some ideas for some even better copy commands. Now, copy isn't super exciting, but it is an important thing in storage systems, and it actually saves you a lot of performance by not having to read data to a host and then write it back to do a copy, and doing that in the storage device itself. But this is kind of stuff that a lot of storage protocols have had, and is not dramatically new. Another thing that we're looking at in NVMe is computational storage. Computational storage has been talked about for a while. Really, the motivation is this. Let's say that you want to do a database query and you had a bunch of SSDs as shown in the top. The way this would typically work is you would read the data from the SSDs into memory. You would have cores on your processor processing that data, and then you would answer the query. And through this process, you get a lot of data transfer. In computational storage, the idea is to move computation to the SSDs themselves. So if you want to do a database query, you would move a portion of that query to the drives. The drives would do the query and then give you an aggregated answer back, which you could then unify and provide an answer to the query. And this really provides three advantages. The first advantage is that, unlike in the example at the top, all of the SSDs can be operating on the query in parallel. So you get the benefit of parallelism. The second advantage is that moving all of the data to memory in the host it consumes power, roughly 5 picojoule per bit to move the data. So if you can keep the data local to the NVMe SSD, you can save power, and power is one of the critical items in data centers. Finally, in the way that CPUs are built today, the memory is typically part of the CPU, and there's typically not full bandwidth to memory for all of the I/O. So by doing the processing local, you get more memory bandwidth. So these are, the benefits of computational storage. What we're doing in NVMe is we're standardizing computational programs. So this is a standardized framework for computational programs. We're introducing a new command set called the compute command set, and it'll basically allow you to operate on fixed function programs. So think of these things like encryption, hashing, those sort of operations, or downloadable programs. You'll be able to download a program to the drive itself and execute it. In addition to computational programs, we need memory to operate on. So we are standardizing subsystem local memory and adding a command set for subsystem local memory. So what you'll be able to do is basically issue a command that transfers data from an NVMe namespace to a memory namespace. You'll then be able to execute a computational program on that memory namespace and then retrieve that data back to the host, or the aggregated answer for that computational storage back to the host. So that's computational programs. That's one way we're looking at accelerating things. Another way that we're looking to accelerate things is, is through something we're calling flexible data placement. Now, since the invention of NAND SSDs, there's been this promise of, hey, if you expose the characteristics of the NAND to the host, you can get better performance. And typically, this can be done to do things like reduce write amplification and improve QoS. And in NVMe, we've been on a journey trying to find the right level of abstraction to do this. So a number of years ago, we standardized IO determinism with the hope of doing this. And IO determinism was great, but it didn't quite solve the problem. Next, we standardized streams. Streams abstracted it too much. So, while you had the ability for the host to control the placement of data on NAND, it was highly abstract and didn't provide the level of control that people wanted. Then things swung all the way in the other direction with open channel and then a thing called Project Denali, which was really kind of exposing the raw NAND to the host. And while that allowed you to get a lot of acceleration and a lot of control, the problem was that you couldn't get interoperable solutions. So every time you change the NAND or the controller, you'd wind up having to rewrite your software. We then went and standardized ZNS, and that's gaining some success in certain areas. But basically, our latest attempt at this is flexible data placement. And we think we now have this level of abstraction correct. So what flexible data placement is what we're doing is we're adding a hint to memory write commands that indicate where on the drive you're going to place the data. And unlike specifying the raw NAND device, what we're really doing is we're abstracting away the geometry of the SSD in a way that's sort of in between exposing raw NAND and a completely abstracted. So with very little software change, you're now able to exploit flexible data placement or host-directed writes. Thank you.
Thank you very much, Peter. Let me turn over control now to Tony Asheri from PlyOps. Tony, you should have control now.
All right. Let's see. I'm going to advance this slide. All right. Good to be with everybody on the call and the esteemed panel. We are a young company out of Israel, PlyOps. But the good news is that both NVIDIA and Intel are investors in us. So it's good to be with both of them, even though Peter is representing NVM Express today. We've heard great stories about NVMe and how good it is, how good NVMe storage is. All of that is good. My perspective today and what I will tell you about is the difficulties of adopting that goodness and what are the challenges with that and what are perhaps some of the solutions, and in this case, domain-specific accelerators, and what a challenge it is to make that easy to adopt in data centers and with solution providers, and what we're doing to make that even easier. So when we talk to our customers, this is generally looking at both the business demand and the data center constraints. So from a business demand perspective, what we hear is there's a lot of new services that are spun up all the time. User growth is there, data growth is there, but environmental responsibility is becoming very prominent as well as far as pain goes. And then at the macro level with the data center constraints, you have the power and cooling, you have DC rack space challenges, you have budget, obviously, and supply chain, surprisingly, is not going away, at least not in certain areas. So with all of this said, people need to rethink how data center needs to be architectured. Going back to NVMe and where we are with that, as you have seen, the performance of NVMe and specifically NVMe SSDs have gone surprisingly very high over time. And not only performance, but the density has improved, the cost has improved. So everything about NVMe storage and NVMe bus is getting better and better. The problem is that CPU and software is struggling to keep up with that. And this is something that is going to, this divide is something that is going to continue to grow. To be more specific, when it comes to adopting NVMe SSDs, there are server architecture limitations itself. You know, all of a sudden, when you get 1000x improvement over HDD in a very short period of time, it's hard to see server architecture being able to catch up with that. There's amplification of data. I think Peter mentioned some of this. Software that uses SSDs amplifies reads and writes by up to 100x. I'll talk about this a little bit more. And then also wastes space. There's a 6x, up to 6x space amplification issue in many of these applications. And then system reliability. The traditional RAID is rarely used with NVMe SSDs due to its huge performance penalty and requires costly workaround. So a little bit more about this amplification problem. As you know, when you tune in something in software and in CPU, you have these processing amplification, you have IO amplification, you have space amplification, you have cache amplification. These are factors that you have to tune in for in software and when you're using CPU and cores to do this. And it becomes, if you tune in for one, well, you're impacting the other one. If you are tuning for, so this is an ever challenge of what do you tune for, and how do you get to a balanced system? And it's a process that it's an ongoing process. So you need to spend software engineering resources on a continuous basis to deal with this challenge. So just to give you one other example of amplification and issues with that, as you know, the world is becoming more and more sensitive to want to realize and look at objects that are not typical 4K, 8K, 128K in trunk size. The world is becoming more 100 bytes, 200 bytes. I'm interested to analyze or look at all these likes that you put in on social media. Those are things that end up being 100 byte transports, in a system that is moving big trunks. So that's a real problem. And to give you an example, in a Redis system, let's say Redis or Cassandra or Mongo, when you're moving a 4K unit back and forth on a TLC drive, if you're interested to analyze 100 byte IO, you end up costing and forcing a 40x amplification. And in QLC, it's even worse because with the 64K indirection, well, that's, let's say in a 1K IO, that ends up being a 64K IO amplification, 64 times IO amplification. So big numbers here. What is the solution? We believe the solution is, by the way, this impacts obviously not only the storage, but the network as well. Think about it, these transports end up, if you're searching for 100 byte IO and your unit of transfer is 128 bytes or 128K over a network, you're wasting a lot of IO going back and forth and not knowing where that object sits. It makes it very, very difficult. So this amplification continues to become even bigger amplification when you're going over the network. So domain-specific hardware acceleration is the solution for this. Rob had some great examples of how that's being solved with DPU. Our solution, PlyOps XDP architecture, PlyOps Extreme Data Processor architecture is very simple. It presents itself as two APIs. One is just a standard NVMe block interface, so it shows up as another storage in the system. And to get really, really big number gains, we also provide an API that a user can include as a storage API in their application. Let's say Redis or Cassandra or Mongo, etc. And there you're talking key value and object directly with storage. So something like RocksDB. I'll get into that a little bit more. We will always run data through multiple transparent hardware engines, and they are indiscriminately trying to compress the data. So in the block mode, that translates to having variable size objects, and it's the IP and our core technology of how we can pack those objects very, very efficiently with the resolution of 1 byte without taking with taking very little CPU or DRAM footprint. This is where it becomes very interesting. And at that point, if you're writing locally to the NVMe SSD very, very efficiently, then adding data protection bits, whether it's RAID 5 or RAID 6 or encryption bits, it's very easy. And because you're indexing the data and you're sorting it and you have a hash of it, you know exactly where the data sits, you know where to go look for it, you know what to rebuild, etc. And this, Peter brought up an example of FTP. Well, this processor and this kind of a technology can provide FTP-like solution for many SSDs, including SSDs that are not FTP compliant, for example. So a little bit more, this is all great, but what does it mean at the end? There is an NVMe problem with storage. There is, i.e. people not being able to take full advantage of it. And there's this hardware domain-specific hardware acceleration. Well, an end user doesn't really know what to do with that. So our solution is, we're not selling, in this case, a hardware accelerator. We're selling an exact solution of how our data shaping technology is going to solve people's problem. So that means data services on top of our XDP data services, XDP data processor, and that starts with XDP RAID Plus, which is the best-in-class data integrity and RAID Plus solution for NVMe and NVMe over Fabric. ExcelDB, which is the best-in-class universal database, and SDS accelerator. These are specifically around OLTP acceleration, database loading acceleration, database backup acceleration, and database analytics acceleration. And XDP XLKB, where an application can include an API and that talks directly to our hardware. And now the gains are in the range of 100x or higher. And we see this used for real-time analytics and ML training solutions. So XDP RAID Plus, we are not compromising anything about NVMe performance. We're giving all of that back. Unlike traditional RAID solutions, we don't slow down anything here, which is the key. People are hesitant to put RAID solutions with NVMe drives, and we solve that problem. Ultra fast rebuilds, as fast as 7 minutes per terabyte. And this is why people are hesitant to put anything maybe greater than 4 terabytes. People are hesitant to put even 8 terabytes sometimes drives in their system. So all that goodness of NVMe solution, but this hesitation to worry about blast radius, worry about rebuild times. This is why we want to put a solution like this to address and increase adoption of denser, bigger, faster NVMe drives. Enhancing SSD endurance, Peter mentioned the whole notion about the FP is the right amplification factor is a big pain. People go through a lot of work to try to reduce that because ultimately drives fail. There's costs associated with life. Over provisioning takes away from economics. You're wrapping dollars around SSD. So if anything you can do to lower the drive write per day headache for SSDs, and do it universally, whether it's QLC, whether it's TLC, whether it's ZNS, all of that. The ability to be able to address multiple single drives. This is very clever. Our RAID algorithm is a distributed RAID algorithm. So We don't need a dedicated drive for parity. We also don't need a dedicated drive for a spare. So we distribute that across the array. And what does that mean? That means that even a spare drive ends up being used as capacity available to the user. And after a rebuild, you can go back to a RAID 5 solution. So going from RAID 5, drive failure, going back to RAID 5. And then fully PFIL protected. This has an NVDRAM solution on board with supercaps that allows for sudden power down scenarios. Specifically with NVMe over Fabric, this is an example of how you can put a XDP on the client side and then decide how much storage on the target side distribute or give to each node. So this is an example of what we did for a few customers in Japan, to be unnamed for now. You'll see some reference to that coming up in the next couple of weeks, but it's exactly that. How do you make NVMe over Fabric adoption easy while providing protection and speed and no compromise with speed? The nice thing about a solution like this is, as you know, somebody like there's not many companies that are specializing in building a dense NVMe over Fabric target commercially anymore. So this could be a white box solution with out-of-box support from any OS. A little bit about ExcelDB. So now, how do you pass some of this NVMe goodness to an end user, specifically the database users? So PlyOps XDP ExcelDB is exactly that. It's tuned to work with solutions like MySQL, Maria, Postgres, even Oracle and SQL Server and Mongo. And the pillars around performance is it gives them 3 to 5x higher performance, 8x latency reduction, 30% better utilization, and 6x better capacity expansion. And finally, ExcelKV, which is where now you add a library to the application to take advantage of that. And for example, a very common library for key value storage for NVMe is RocksDB. So we've made this very easy, including our version of RocksDB. We call it XDP Rocks, that allows for seamless integration with the application. So something like Redis or Mongo Rocks or a lot of other applications out there can just seamlessly work with our hardware, get 20x more throughput, 100x better latency, 10x better CPU utilization, and 6x better capacity expansion. Thank you.
Thank you very much, Tony. Let's go to the first panel question here. 1 second. Okay, and our first panel question is, we'll start with Rob, then go to Peter, and then Tony. The question is oh, this is not the right question. Sorry about this, guys. Hold on. Let's go to the second question here. What are the greatest challenges that companies are likely to encounter when exploiting and deploying acceleration? And what are some of the tips or best practices they can utilize to avoid these issues? Peter, why don't we start with you, then we'll go to Tony, then to Rob, please.
Sure. Thanks. So acceleration isn't new. It's been around since the history of computing, back to accelerators for VAXs. This has gone back and forth. Somebody would develop an accelerator, piece of silicon, then that acceleration function would get sucked in the CPU, and then some new capabilities would emerge and the acceleration would go out, and this would go back and forth. I think we've seen now that with the slowing of Moore's law, we're probably at a point where acceleration makes sense outside the CPU, and it's here to stay for a variety of applications. The big issue with acceleration is aggregating requirements onto something that's broadly useful in the ecosystem, right? So where there's a real market. I've worked on NVMe controllers for 15 years, and they were highly programmable, and people would accelerate all sorts of things, but they were in very vertically integrated markets. It wasn't something that somebody could widely share. So really the challenge is less about the technical piece of accelerating and more about the economics. And I think that in the changing ecosystem with the slowing of Moore's law, we're going to see more and more acceleration. But the key is to accelerate the type of applications that can be aggregated together and create a market, and also providing the flexibility, because once you've accelerated it, everybody then wants to differentiate.
Great points. Tony, what do you guys think about that from Plaib's perspective?
Yeah, I agree with everything Peter said, and it was the whole notion of what I presented. It's not a business of selling acceleration; it's a business of selling solutions. So for our case, it's these data services that run on top of a accelerated engine that is doing data shaping for NVMe drives. So that is really the key. And it starts for us, for example, it starts with a basic notion of best NVMe data protection. And then how do you use them? There's no, for an end user that is looking for database loading improvement or database backup improvement, well, that is the pain that we're solving. It's not, placing a data accelerator for them not knowing what to do. So the purposeful solutions out there, and it starts with some macro function like data protection, but when it moves to the database, it becomes very specific around, for example, the four factions that I mentioned. But even moving above that is about how do you improve metadata and analytics for short video processing. So that is the way to approach this, and being close to the application and having ISVs and ecosystems supported, it's even better.
So Rob, obviously NVIDIA has done a lot to accelerate a lot of different workloads in a lot of different spaces. What do you guys see as kind of some of the best practices here?
So the biggest challenge, I said in my talk, we love acronyms in our industry, and the acronym here is SMOP. It's an old one. It stands for Simple Matter of Programming. And the biggest challenge to adding accelerators is the integration into the current software stacks. And that's why at NVIDIA, we developed a framework called DOCA. We have a similar framework called CUDA for programming GPUs, and DOCA is designed to make it easy to program, test, and debug the DPUs and all their accelerators on NVIDIA Bluefield.
Very good. Let's go to the first audience survey question. I'm going to launch that right now. The question is, are acceleration technologies something that your company or organization is currently exploring? This is a pick all that apply. We'll leave the window open for a couple of minutes and just click whichever ones apply to your organization. Again, the answers are anonymous, so you don't have to worry about exposing yourself, so to speak. And with that, let's go to panel question number 2. We'll start with Tony, then Rob, then Peter. And that question is, do any of you see, I'm going to call them forward-looking technologies. CXL is one example of that, but there are other ones that are kind of coming out too. How important are these for storage, networking, or data processing acceleration? And kind of what role do you think they'll play going forward?
Again, we like it from an application angle and that perspective of how do you use an acceleration engine and sort of an offload island, if you want to call it, to address the application's need. One example is how you provide an NVRAM pool to an application through the CXL interface. This is something that we have in our technology and in our IP. And to be more specifically, how do you use a write-ahead log with the CXL interface seamlessly to an application?
Thank you, Rob. What do you guys think about CXL or other technologies like that?
From a storage perspective, we think that CXL has potential as a system or rack level storage tier, with NVMe over fabrics behind it and hard drives and then tape, the standard tape or tiering process. I say potentially because many of these network bus replacement technologies have come and gone over the 40 years I've been in this business. We had NGIO and Gen Z and et cetera, et cetera. And underneath CXL is PCI, and there have been many attempts to turn PCI and other bus technologies into networks over the year. Peter and I have discussed this often at Flash Memory Summit talks that we were both on. And so many companies have worked on it. A lot of them actually got it to work if you put the PCI switch in the middle of the rack. But is that really a network? I don't know. I guess it is if you're interested in just networking within the rack. But it's definitely, CXL is definitely good technology for, in the rack, in the system box, and around storage, particularly for adding a faster tier between DRAM and NVMe storage, SSD storage.
Yeah, well put. I would agree with that 100%. Peter, it sounds like you would as well.
Yeah, absolutely. Around CXL in general, CXL for direct attached memory, I think that's going to be super exciting. It allows people to add a memory tier, either slower DRAM or non-volatile memory to standard devices. So that I think is super interesting. Memory pooling and memory sharing, I think first and foremost, that's a TCO play. If you look at it, memory has become an increasingly larger fraction of a server BOM. And people are looking for ways of, hey, how can we reduce that by statistically sharing or eliminating stranded memory? So that's really the primary play for pooling. But with that, what it does is it basically creates memory that accelerators can access as a first-class citizen rather than it being stuck on CPUs. So it enables all sorts of acceleration. But, I think there's a lot of innovation in this space. We'll need to see how it plays out. We've kind of been here in the past. I don't know if anybody remembers, PCI Express multi-root IO virtualization that was supposed to share and disaggregate storage and networking. It didn't take off. A couple other things to think about is, memory pooling and sharing moves memory further away from the processors. So that added latency will have an impact on performance. So, that'll be important to understand what applications can tolerate that. And finally, I think there needs to be a balance. Not all memory can be pooled, because pooling memory means you're pulling it through a fabric or a network, which increases power. And, again, power is super important in data centers.
Great points. And I remember multi-root IO virtualization very well. So we'll have coffee about that sometime.
Mm-hmm.
With that, let's go to the third question here. Sorry. Or the second audience survey question is, what type of workloads in your organizations are candidates for acceleration? Pick all that apply. I'll go ahead and launch that while we do the Q&A session. And with that, let's go to the first question. And that is, this one is for NVIDIA. What form factors are the NVIDIA DPUs available
in? They're standard PCI form factors, half high, actually full height, half length. I think it actually depends on the Bluefield. So with Bluefield 2, there's half high, half lengths. Bluefield 3s are just starting to come out, so I don't know if there's any official information on that yet. You could check our website. And then so it really depends. They can be implemented on all different kinds of platforms as well, from a chip perspective.
Thank you. Good deal. The next question we have is how to utilize DPUs in existing virtualization, i.e. vSphere or KVM or K8 platforms. Are there existing or planned support? Rob, you want to start with that one? I think you said you want to answer that one. Now we can go through everybody else.
Okay. Yeah, sure. So if you were to Google NVIDIA VMware Bluefield DPU, you would get a lot of information on that. So VMware is actually partnered with NVIDIA to implement vSphere on the, or parts of vSphere on the DPU to accelerate it. As far as containers go, I would look at the Doka, like NVIDIA Doka containers or something like that. And you should be able to get a lot of information on that because Doka is going to be able to support that.
Excellent. Tony, anything on your guys' side as far as existing virtualization schemes that you work with or anything like that?
Today we support vSAN Direct, so we are in that setup as well as any other Linux-based virtualization. And then we are looking at adding physical functions and MFND and so forth in our next generation processor. So not a showstopper for us, although we see a lot of bare metal in our world and a lot of orchestration in our world more and more. So.
And Peter, I'm going to assume that NVMe supports all these capabilities as well, right?
Yeah, we've got virtualization standardized in NVMe. We're also working on live migration to allow you to migrate, across controllers on different subsystems. So that's something we're working on.
Outstanding. Let's see. And with that, we have one more question. Peter, you talked about computational storage, and you talked a little bit about encryption. Are there other workloads that people are seeing computational storage being important for?
It's database acceleration, encryption, file system acceleration. There's a whole myriad of applications.
Excellent. Thank you.
I would add to that the edge. One of the problems with the edge is you get a lot of data. Think of like a video, you're in a security system, and moving all that to somewhere that can analyze it is hard because it's the edge and you don't have the kind of connectivity you have in the data center. So we think at NVIDIA that the edge is a prime place to use artificial intelligence or for computational storage kind of applications.
I think that's a great point. I mean, you think of a car, you really can't put a one-use server inside of a car very easily. Makes a lot of sense. All right. And with that, guys, I think we've hit the top of the hour. Again, thank you, Rob, Tony, and Peter for participating. I think these were great questions. Thank you, audience. Again, we have recorded this. We'll provide the recording and the PDF of the slide set to everybody who registered in the next couple of days or so. And with that, again, thank you very much. Have a great day and looking forward to seeing you all in the next webinar we have.